of the universe using measurements from scientific instruments. So I'm interested in understanding how the universe formed, how it came to look the way it does. And there's a lot of different approaches that people can take to answering these questions, such as more theoretical approaches, doing math, kind of using Einstein's equations to understand the evolution of the universe. I'm specifically interested in making measurements and seeing what these measurements can tell us about the early universe. And I do this from the Owens Valley Radio Observatory, or OVRO. OVRO, as the name suggests, is located in the beautiful Owens Valley of California. If you haven't made it out to this part of the state, I highly recommend it. It's about a 4-hour drive from the LA area, and it's located near the Big Pine and Bishop towns, between the Sierra Nevada mountains and the White Mountains. So OVRO is a large radio observatory with many different projects going on at any given time. You can see that there are a bunch of different telescopes, dishes, antennas on site. Probably the most impressive looking is this 40-meter dish right here. But the instrument that I work on is the one shown in the foreground here. So it's an array of these radio antennas shown here. They're sort of these pyramids made out of aluminum. And I'm going to explain how I use those to do cosmology measurements. So this is just another photo of the array. You can see that there's many of these antennas. There's actually 352 total spread over a 2.5 kilometer range. And you might be able to pick out some people in this photo here. This gives you a scale of the antennas. They're about 5 feet tall, each of them. So this is a brief outline of the talk. I'm going to start off by giving some background of the history of the universe as we understand it. Next, I'm going to present some key principles of observational cosmology. So these are kind of the guiding principles that we use to study the universe. Next, I'm going to talk about hydrogen and why it's so important for this kind of work. And then I'm going to talk about the telescope, the OVRO LWA. So starting off with a history of the universe. So you all may have seen an image that looks something like this before. So this is a plot of the evolution of the universe, starting with the Big Bang on the left here. And this, the scale of this plot is supposed to represent that the universe is expanding. So the Big Bang occurred about 13.8 billion years ago, and that commenced the universe. Right after the Big Bang, the universe expanded extremely rapidly through a process we call inflation. And this early universe was very hot and dense. And so it existed as a state of matter called a plasma, which is, again, hot and dense, and it glows brightly. And the universe was opaque at this point. This all changed nearly instantaneously after about 400,000 years, when the universe finally expanded enough, it cooled enough that it ceased to be a plasma. And this is the first moment that the universe became transparent. And this produced this afterglow light pattern. You might hear this referred to as the cosmic microwave background, or CMB. So after the universe became transparent, we entered what we call the dark ages. And they're called the dark ages because there were no bright luminous objects in the universe, no stars and galaxies. So the universe was basically suffused with hydrogen gas, maybe a little bit of helium, but no stars and galaxies, nothing bright that we could observe. But as the Dark Ages progressed, this process was happening where clumps of gas were coalescing under the force of gravity. So you would have an overdensity of gas that would clump together because of gravity. And ultimately, after several 100 million years, these clumps of gas became dense enough that they reignited, producing stars and galaxies. So this is when the first stars appeared. This was sort of a gradual process over time where more and more of them appeared. And finally, that brings us to the development and evolution of galaxies and planets. stars would die and be reborn. And that brings us to the modern day. So in the modern day, we see many stars and galaxies around us. So I'm particularly interested in understanding more about these dark ages and the formation of the first stars. So this is the focus of my research. Questions that I want to ask are, when did the first stars turn on? How big were the first galaxies and black holes? What was the temperature of the early universe? And what is the universe's expansion history? So how fast was it expanding? How fast is it expanding now? And how fast has it been expanding over time? And understanding these kinds of things could answer big questions about the physics that governed the early universe, the nature of dark matter, what was going on with dark energy, all of these really uncertain things that cosmologists want to understand better. Okay, so this brings us to the key principles of observational cosmology. So one of the first principles is that light is a wave. So if we imagine a distant object, say a star, this star produces light. Light is electromagnetic radiation that manifests as a wave with a particular wavelength. And the wavelength of that light determines the color of the light that we see. Any given star or galaxy or astronomical object generally produces several different wavelengths or colors of light. And so with our telescopes or potentially with our eyes, we detect all of these different colors, and we can piece them all together to get a pretty good understanding of what we're looking at. And so this is how astronomy works. We get all of these different wavelengths, these colors of light, and we therefore deduce what's going on in the star and the galaxy that we're looking at. So these different wavelengths of light exist on a continuum. And so we can see here just an image of different colors of light, where over on this side, we have purple light, has the shortest wavelength. And then moving through, we have red light, has the longest wavelength over here. So this is what we call the spectrum of visible light, all of the colors that our eyes can pick up. However, there are many wavelengths that our eyes cannot pick up. So beyond the visible light spectrum, we have wavelengths of light that are too short for our eyes. So this includes ultraviolet light. Beyond that, we have X-rays. And beyond that, we have gamma rays. So these are types of light that have very, very short wavelengths. On the other side, we have wavelengths of light that are too long for our eyes to pick up. So this includes infrared light. And then beyond that, we have radio waves. And so our eyes cannot detect these, but we can build specialized instruments that can see these different types of light. For example, we can make an image of the sky in the visible spectrum. So this is the kind of light that our eyes can see. This is just an image of the full sky. You see the galaxy here in the center. And this is much like what we would be able to see on a very clear night or something like that, looking up at the Milky Way. However, we can make a similar image of the sky using wavelengths of light that are too short for our eyes to see. So this is an image of the sky produced with X-rays. So an X-ray telescope was able to reconstruct this entire image. And beyond that, we also have gamma rays. So this is an image of the sky using gamma rays. On the other side, we can use telescopes that are tuned to detect light with wavelengths longer than visible light. For example, this is the infrared sky. This is the microwave sky. And then at even longer wavelengths, we have the radio sky. And this is my focus. So radio astronomy uses telescopes that are tuned to very long radio waves. And we can learn a lot about what's going on the sky in astrophysics using these long wavelengths. Okay, so that's the first key principle of observational cosmology, that light is a wave, that these different colors of light have different wavelengths, and that not all these wavelengths are visible to the human eye, and yet we can build instruments to be able to see them. The second key principle of observational cosmology is that light takes time to travel long distances. So light has a speed, a finite speed that is shown here in miles per hour. So you can see that it is very, very fast. But nonetheless, things are very spread out in the universe. So even with light moving so fast, it can take quite a while for this light to go from place to place. For example, it takes light from the sun 8 minutes to reach us. And so you may have heard if the sun were to, magically go out one day, it would take us 8 minutes to know that something was even wrong. Proxima Centauri is our closest star, as the name would suggest. In kind of astronomical distances, it's quite close, and yet it takes light from Proxima Centauri 4 years to reach us. The center of the Milky Way is 26,500 light years away, which means that even in our own galaxy, it takes light from the center 26,500 years to reach us. And the Andromeda galaxy is over 2.5 million light years away. So when we look out at the Andromeda galaxy, we're seeing it not as it looks right now in the year 2022, but how it looked 2.5 million years ago. And we can kind of take this effect to its extreme as we look further and further out in the universe. So if we imagine using our telescope to look in the vicinity of our Earth, we see our own Milky Way galaxy. Looking out beyond that, we see nearby galaxies. And then further beyond that, we see more distant galaxies. And these distant galaxies are going to appear as they did potentially millions, hundreds of millions, billions of years ago. If we look even farther, we can look at things that are so distant that the light from them actually predates stars and galaxies. So this is looking back into this dark ages stage before stars and galaxies were formed. And I just want to emphasize that this image here is not what the structure of the universe is. As far as we know, the universe is pretty homogeneous. We could go anywhere in the universe and it would look much the same. This is just how it appears to us because of this finite speed of light. Whereas we're looking farther and farther out, we're seeing the universe as it appeared longer and longer ago. And this was really put into practice with the discovery of the cosmic microwave background, or CMB, in 1964. So this was a discovery with this radio telescope in New Jersey called the Holmdel Horn antenna. And they discovered that there was some radiation, some light at millimeter wavelengths coming from all directions. And what they discovered was that this was actually the afterglow of the Big Bang. So this is light from that moment when the universe first became transparent. And it is so distant that it is coming from almost 14 billion years ago. And this really kicked off a flurry of discovery in observational cosmology, specifically with 3 satellite-based telescopes, first COBE, then WMAP, and then Planck, that made successively more precise measurements of the cosmic microwave background. And what they found is that while this background is very uniform across the sky, it's almost nearly uniform everywhere, there are some small fluctuations in the temperature. And so what we see here is that the orange spots are slightly brighter regions on the sky, and then the blue spots are slightly dimmer regions on the sky. And studying these fluctuations in detail has given us a lot of insight into the physics that actually governed the early universe and the Big Bang. So this led to an understanding, that the universe did begin in a Big Bang sort of event, that it likely underwent inflation after the Big Bang, and this sort of stuff. So just a wealth of information in this kind of random looking map here. We can also do science using the polarization of the Cmb light. So light has a polarization, which just means that polarization refers to the alignment of the waves. And there's a lot of experiments that are currently undertaken that are aiming to measure this polarization. So examples of this are the South Pole Telescope, the BICEP 2 telescope, and the Keck array that are all located near the South Pole in Antarctica. And this is a great place for them because the air is extremely dry and the atmosphere is thin, and this enables us to do this kind of science. So that is the second key principle of observational cosmology. We can study the early universe by looking for light from very distant sources. And the last principle of observational cosmology is that the universe's expansion distorts light. So once again, if we imagine a star and our telescope is measuring the light waves from that star, but we then consider that that star or potentially that galaxy is very, very far away. Recall that the universe is expanding. And so as that light travels to us, it's going to be expanded and the light wave is going to be stretched. So what this means is that for that very distant object, if it's emitting yellow light, that light might appear to us as red because the wavelength has been so stretched that it has shifted color. And we call this effect red shifting. So light from these distant objects is stretched. And this occurs for any color, any wavelength of light. It doesn't even have to be visible light. We expect that light from distant objects is going to appear to us at a longer wavelength than it was emitted. Okay, so now I'm going to talk about hydrogen and why it's my favorite element, and it enables us to do this kind of observational cosmology. So hydrogen is really the key to understanding the dark ages and early star formation. If you imagine the periodic table of all of the elements, hydrogen has a special place in the upper left because it's the simplest element there is. It consists of just two particles, a positively charged proton and a negatively charged electron. And it's by far the most abundant element in the universe. So let's talk about the composition of the universe real quick. So the universe is only 5% ordinary matter. So by ordinary matter, I mean the stuff in the periodic table, everything that makes up ourselves and the things around us. 68% of the universe's composition is dark energy. So this is sort of a mysterious type of energy that's driving the expansion of the universe. 27% is dark matter. Dark matter is matter that has mass. It interacts via gravity. We know it's out there because it's very important for the structure of galaxies as we know them. But we're not quite sure what it is. And there's a lot of experiments trying to directly measure what particle makes up dark matter. Yeah, so the dark matter and dark energy are kind of mysterious, unknown aspects of the universe, and then ordinary matter is just a small 5% slice. And out of that ordinary matter, a whopping 73% is hydrogen. So the vast majority is hydrogen. A further 25% is helium. Helium is the next simplest element in the periodic table, and everything else is just 2% of all matter. And where is this hydrogen? About half of the hydrogen in the universe is contained within galaxies, but the other half is between galaxies in the so-called empty space. So this is kind of counterintuitive. We expect that empty space is truly empty, but it's not. There is some stuff out there, and we call this the Intergalactic Medium, or IgM. The IgM has a density of 1 atom per cubic meter, which is very, very low. Just for context, on Earth, there are this many, I don't even know how to say this number, atoms per cubic meter. So there's really not a lot of stuff in this empty space, in this IgM, but there is some. And because space is so large, this can add up to being an appreciable amount of hydrogen. And my research focuses on this hydrogen in the IgM and understanding what it's doing in various stages of the universe's evolution. So hydrogen exists in 2 states. First of all is the neutral state, and we call it neutral when the proton and the electron are bound together. And then in contrast, the ionized state is when that bond has been broken, when the proton and the electron are able to move independently of one another. Neutral hydrogen is also called H1 by astronomers. Like I said, the proton and electron are bound together. And the key point for radio astronomy is that it glows very faintly at radio wavelengths. This glow has a very specific wavelength of 21 centimeters. And then ionized hydrogen is also called H2. This is, again, where the proton and electron are free from one another. And neutral hydrogen can become ionized when it's hit by a particle or a bit of light. This particle can kick the electron off of the proton and cause hydrogen to become ionized. So during the dark ages, the hydrogen in the IgM was neutral. So all of the protons and electrons were bound together. But this all changed with the formation of the first stars and galaxies that gradually ionized this hydrogen. So these first stars and galaxies produced all of this light. All of the light propagated out in the IgM and kicked all the electrons off of the protons, ionizing the hydrogen. Currently in the present universe, the IgM is completely ionized, so any neutral hydrogen is going to exist within galaxies. And we want to understand this transition better. So understand how these first stars and galaxies ionized hydrogen in a process called the Epoch of Reionization, or EOR. So this, if this video will play now. There we go. So this is just a simulation of the Epoch of Reionization, or EOR, process that was developed by some theorists. So what we're seeing here is the simulations kind of progressing through early star and galaxy formation. And we see these bright regions here are ionized bubbles. And these bubbles are sourced by a galaxy that's producing all of this light that's propagating out. And you can see that this is a really patchy transition. So as more galaxies form, as their light has more time to go further and further out through space, we see these ionized bubbles start to grow more and more. And then these darker regions here are the residual neutral hydrogen. And as the simulation progresses and at the ends, you'll see that that neutral hydrogen completely disappears. And this is when the IgM has become completely ionized. Right, so this is kind of what the modern day universe looks like, where we have these bright galaxies, and then between them, we have ionized hydrogen. Okay, so like I said, because of the redshift effect, the light that's emitted by neutral hydrogen is emitted at 21 centimeters, but we might observe it at much longer wavelengths because of the expansion of the universe distorting that light. So if we look very far out into space, beyond all of the modern galaxies into these first galaxies, we may be able to detect this 21 centimeter line from neutral hydrogen during the dark ages and early star formation. But this signal is hard to detect because it's so distant and it's quite faint. And the wavelength of light that we measure actually gives us the distance. So if we see a wavelength of light that's quite long, that indicates that the hydrogen is very distant, whereas a slightly shorter wavelength lets us know that that hydrogen is closer to us. So this is really neat because it could potentially allow us to do 3D mapping of neutral hydrogen throughout the early universe. So we'd be able to make an image of all the neutral hydrogen on the sky at each phase in the evolution of the universe. Okay, so that kind of explains why we care about hydrogen so much. Now I'm going to talk about how we're attempting to make this measurement using the OVRO LWA. So once again, this is a picture of the OVRO LWA, or long wavelength array, consisting of all of these different radio antennas spread out over a large area. So the overall LWA is a long wavelength radio telescope. So if we imagine, again, the whole spectrum of different wavelengths of light, it exists out here. So in the radio waves, kind of similar to what kind of wavelengths your radio uses to transmit FM broadcasting. So these are very long wavelengths. They're wavelengths of 3.5 to 25 meters. Just to give you a little visual of what that might look like, this is a stick figure indicating a typical sized human. And then here is an indication of what 3.5 wavelengths would look like. And on the bottom, we have 3.5 meters. And on the bottom, we have 25 meters. So these are absolutely enormous wavelengths. How this instrument actually measures these wavelengths is using a technique called interferometry that's commonly used in radio astronomy. So we talked about how there are many, many antennas in this array that composes the full telescope, and pairs of antennas work together to make the basic measurement. So we take the voltage signal from one antenna and we multiply it with the voltage signal of another antenna. And this produces our basic unit of data called a visibility. We then have many, many antennas, and we do this with each pair of antennas. So one antenna with every other, another antenna with every other antenna. So this produces many, many visibilities. And then we do signal processing of all these visibilities to get a pretty good reconstruction of what was going on the sky. So just another image of this telescope, again, just showing how many of these antennas there are. So the overall LWA was built in 3 stages. In its earliest incarnation, from 2013 to 2014, it had 256 antennas, 251 of which were in this compact core. So this is just an aerial map of the array. You see that most of them are clustered together in this 200-meter region. And then there's also 5 what we call outrigger antennas that are further away. And these are important because we need large separations between antennas to achieve good resolution in our instrument. The stage 2 upgrade occurred between 2015 and 2020, and this added 32 antennas that were all outside of the core of the array. They were so far away that they were connected via fiber optics. So there was a lot of new technology developed to enable this. And this is what the layout looked like. So these blue lines here are indicating the new fiber optics that were laid in the ground to support the new antennas. We're currently undergoing the stage 3 upgrade that commenced last year, and we're currently constructing it. We expect it to be complete very soon here, probably within the next couple months. This brings the total number of antennas in the array to 352, with the addition of 64 additional antennas. So we now have 243 core antennas and 109 outrigger antennas that are further away. With this upgrade, we've also completely overhauled the data processing back end, so the analog and digital back end, and overhauled the way we analyze data. So all of this gives us more sensitive measurements, improved resolution, and we expect to be getting higher fidelity images out of the new array. So this is just an image of me. This was last summer out on site participating in the upgrade. This also gives you a scale of how big these antennas are. I'm about 5 feet tall, so I require a step stool to work on them. Others don't. But each antenna here has a circuit board in the top, and this circuit board is going to measure the signal from the arms of the antenna and amplify it before that signal is run either through a coax cable or a fiber optic for further processing. So here we were just removing these circuit boards from each of the antennas in order to clean them and test them before we reinstalled them. So this is just a close-up of what the inside of one of these antennas looks like with the circuit board. And this also motivates why we needed to clean all of these for the upgrade. So it turns out that the central hub of these antennas is a prime habitat for spiders and other insects. So we opened up a lot of the older antennas and they looked like this inside. So each of these antennas has produces two signals, one from each polarization. So the polarization just refers to the orientation of the arms of the antenna. So you have a north-south pair and then an east-west pair. We take a voltage from each of these and then run it back to the shelter where we do the further data processing. So if you imagine we have 352 antennas, each producing two signals, we have 704 cables taking all of those signals back. And this is just an example of what that looks like. So cable management is really key for this telescope. And once again, here I am plugging in some cables. And this telescope is really uniquely suited to measuring this cosmological hydrogen signal. So the 21 centimeter signal from neutral hydrogen in the early universe. And it's so well suited for doing this because it's one of the few telescopes that actually operates at these very long wavelengths. So many radio telescopes look at radio waves that are shorter wavelengths, but this one goes all the way out to these very long wavelengths. It has many antennas, which gives it excellent sensitivity and resolution, which is key because we're looking for a very faint signal. And then also with the upgrade, we have precision electronics that also improve the sensitivity of the measurements. However, despite all of this, measuring the signal is still really, really hard. And this is because, again, it's so faint, it's so distant, and we have all of this intervening stuff between that signal and our telescope. So if you imagine this cosmological hydrogen signal we're looking for, from almost 13 billion years ago, between that signal and us, we have all of the intervening galaxies. And unfortunately, these intervening galaxies also produce radio waves. They produce light in the radio spectrum. So we're going to see that overlaid on top of the signal we're looking for. We also have our own galaxy, the Milky Way, once again, produces radio light. So this is lying on top of that image that we want to make. And these intervening galaxies in the Milky Way together at radio wavelengths are over 1,000 times brighter than the signal we're looking for. So you're trying to find something, very faint that's also obscured by something bright. So it's quite difficult in that way. We also have our atmosphere, particularly the ionosphere, will distort our signal and pose challenges. We also have the cosmic microwave background is backlighting all of this. And then we also have human-made radio frequency interference. So all of your, radio broadcasting, telecommunications, satellites, things like that, that produce radio waves, that signal can get into our telescope and contaminate the measurement we're supposed to be making. So the key to doing this kind of science is we need to be able to filter out all of these other signals and focus just on what we want to see, which is that cosmological hydrogen, that hydrogen from very long ago. So in that search for this cosmological hydrogen signal, what we actually end up doing is learning a ton about all the other stuff, learning a lot about RFI. How does that actually look? Where does it come from? Learning about our ionosphere, the atmosphere, what does that look like day to day? We do extremely precise mapping of the Milky Way galaxy, all of these other galaxies. We use these galaxy surveys to try to subtract out their effect in order to improve our ability to see this distant hydrogen signal. And we can also play some clever tricks. For example, we know that the light from intervening galaxies in the Milky Way tends to appear at a lot of different wavelengths, whereas the hydrogen signal appears at specific wavelengths. And so we can use that kind of thing to use signal processing techniques and try to filter out all of the intervening signals and get at what we care about. So what's the current state of the field? We've not yet measured this hydrogen signal. So we're working very hard on it. We hope to achieve a measurement soon, but it has not been measured by this telescope or really any telescope. So where we are now is we're placing upper limits on the signal brightness. So this is where we know how sensitive our measurements are. We're constantly improving their sensitivity. And we still haven't seen anything. So that lets us know that the signal we're looking for is fainter than what we would be able to detect with our telescopes. And this allows us to do some science. You know, there's some ideas of physics of the early universe that would produce a very bright signal, and we can rule those out right away because we would have seen the signal had that been the case. However, we really want to achieve this detection so we can measure exactly where neutral hydrogen was before and during the formation of early stars and galaxies. And that would just give us a wealth of knowledge about what was going on in the early universe. Yeah, and so my job now is just improving the telescope, improving our data analysis techniques, and hopefully achieving this measurement. Okay, and I'll stop with some concluding thoughts. So observational cosmology is this very powerful tool for understanding the origin and structure of the universe. This light from neutral hydrogen opens up a window into the dark ages and early star and galaxy formation. We're hoping to measure the signal with the overall LWA, and these measurements would explain how the first stars and galaxies formed, give us clues about dark matter and dark energy, black holes, and other physics. And this is just an image of the LWA team. Here we're standing on the catwalk of the 40-meter dish at the Observatory. Yeah, and finally, I just want to acknowledge that the LWA team is a very large collaboration split between many different institutions. And also thank Steve Flanders, the Palomar Observatory, and this Greenway Talk series for enabling me to be here today. And with that, we can transition to taking questions and having a bit of discussion. Thank you.
Okay, I'll ask the first question.
Yeah.
This is low band of VHF. Would you benefit from a radio quiet zone like Green Bank uses?
Yes. So there's some idea that yeah, if we were in a more radio quiet region, that would improve our measurements. So unfortunately, we don't have the ability in the Owens Valley to really enforce, you know, a lot of radio quiet stuff. It's too densely populated for that. But yeah, certainly if we could pick up this telescope and move it to somewhere really remote or somewhere with a strictly enforced radio quiet zone, that would improve our RFI problems.
Well, I'll ask another one. So, okay, so, and I think somebody else picked up this question too. With these wavelengths, would it be feasible to develop a space-based antenna or maybe put it on the moon or, you know, get into a real quiet area?
Yeah, absolutely. So there's been a lot of inquiry about whether we could build an array like this on the far side of the moon, really for RFI mitigation reasons, because then you have the moon between the Earth where we're emitting all of these radio signals. And so the moon would shield the telescope from those. So yeah, that would be great. Obviously, it's very expensive and difficult. So all of those ideas have kind of been in the, you know, I don't know how practical it is to expect that we are able to build an array on the far side of the moon. But yeah, there's been a lot of inquiry about how feasible that is.
So I don't know much about electronic filtering and all, but you said that your signal was something on the order of 1,000 times less than the background. With all the expertise at Caltech, can't you knock down that 1,000 times to I don't know, to some much, much, much smaller number?
Certainly, yeah. Yeah, and that's what we do. So, right, so the 1,000 times metric is just looking at the total power of each of these signals. But what we do in the filtering is we go in and we remove anything that is what we call spectrally smooth. So this is things that appear at many wavelengths. So maybe for folks who know more about signal analysis in the audience, what we do is we Fourier transform across frequency, and then we cut out the lowest mode. So we're only looking at things that are very spectrally variant. And this preferences our signal over what we call the foregrounds, which is the Milky Way and the intervening galaxies.
Isn't there some way that you could somehow beat an artificially made 22 centimeter signal against your signal and further enhance it? I mean, is that a technique? I mean, I'm maybe showing my ignorance of signal processing here, but maybe is that a technique that could be used, some sort of beating the signal?
Heterodyning.
Beg pardon?
They call it heterodyning.
Heterodyning. Okay. You know, maybe that's another way to increase this. I mean, I think, you know, everyone on this call is going to be in their dotage. Some of us already are, before any antennas are built on the moon. That's just not a practical solution.
Right, and antennas on the moon also don't solve the problem of you know, astrophysical foregrounds. So you're still dealing with intervening galaxies, you're still dealing with the Milky Way. It only buys you better RFI performance. Yeah, sorry, I'm not familiar with this heterodyning technique. I will say that we've done a lot of work, you know, injecting, artificial 21 centimeter signals in. So creating simulations of what the signal might look like, putting those into our pipeline and seeing how robust our analysis is to those signals. You know, we can tweak a lot of knobs. We can say, we don't know the galaxy emission that well. So if we include some uncertainty there, what's our ability to recover the simulated signal? You know, we do have to be careful to not bias our measurements. So we don't want to expect the signal to look like something and thereby you know, produce a measurement that corresponds to that, that's not necessarily incorporating real information from the signal. Yeah, so there's careful analysis and careful statistics trying to answer exactly these questions.
So heterodyning, what that does is you mix the signal coming in from your telescope with a local oscillator that's well controlled and the frequency is known, and it down converts the band that you're looking at to a set of lower frequencies. Generally, this is done to enable utilization of components that are, say, of higher performance or give you better signal processing capabilities than you would have at the higher frequencies. So I'm thinking that maybe given your low frequency, you know, band that you're looking at, maybe I would think that at those frequencies, you could even probably buy off the shelf A to D converters and go almost RF detection to digital. So I'm not sure how much, you know, heterodyne might buy you. Your real problem is to filter out noise sources. So, you know, if you could get down to, you know, narrowing your bandwidth by down converting, it might buy you something. But yeah, I've got to think that with all the folks at Caltech, there's probably, you know, 1,000 people there who know about those sort of techniques. So if nobody's proposed it, they maybe didn't see a benefit.
Yeah, absolutely. Yeah, so my expertise is more on the data analysis side and less on that kind of first order data processing and digitization. But I certainly work with a lot of experts on that. And we have, you know, a custom built analog backend, custom built digitizers, and I'm sure they're incorporating a lot of those techniques.
Sure. I have a question. So that cool simulation that you showed, was that fully relativistic or was it just Newtonian gravitation?
I'm not sure actually.
All right, no worries.
Yeah.
Just curious. I'm like somebody said, a lot of us are like really old people. And so when I was an undergraduate, one of my differential equations professor had a brother who was doing Newtonian gravitation simulations of, many particles. Of course, back in those days, I think he only could do like 1,000 or something. And he actually showed spiral galaxy formation just using Newtonian gravitation. So it was pretty cool for the time. Now you could probably do that kind of stuff on your phone.
Yeah.
Other questions?
I think that the Air Force has a lot of expertise in doing things like this, but I'm guessing most of it is classified.
Well, most of us do this kind of work with signals that we have developed ourselves for specific purposes. So this is looking at natural signals, which you didn't have a chance to construct it and construct the bandwidth and the polarization to help you detect it on the other end.
Right.
So
yeah, there's a lot of overlap though. And actually one of our problems is that satellites, even when they're not producing their own RFI, they will reflect RFI from the Earth, and thereby, get RFI into our telescope that may have been emitted over the horizon. But I know people who've worked in collaboration with me who've actually flipped this on its head and said you can use these RFI reflections to measure satellites and actually map where they are, which has a lot of defense implications and stuff like that. So I think they got a government contract to do that kind of work with our telescopes.
Yeah, that is a technique. Does polarization help? If you kind of control the polarization of all these antenna pairs, can you find signals that you might not have found if you're just isentropic?
Yeah, so there's a lot of science you can do with polarization. Maybe unfortunately, this hydrogen signal is unpolarized, or we expect it to be unpolarized. So we can't filter out based on that. And it's actually worse than that because there's plenty of intervening polarized stuff, and that can complicate our analysis because linear polarization specifically tends to be very frequency dependent. And our filtering is all based on this idea that we're looking for something frequency dependent when we expect the contaminating signals to be frequency independent, but then suddenly we have polarization as frequency dependent. So a lot of my work has been using polarization not to look for the hydrogen signal, but to look for emission from the Milky Way and understand it better so that we can subtract it out.
Is that constellation of Starlink satellites that Mr. Musk is going to throw up in the sky, is that going to make your job more difficult?
Yes, we are concerned about that and the RFI implications of that.
Are you worried about multipath from the satellites like you talked about before, or do we have sufficient guard bands to protect the signal?
Yeah, so the Starlink satellites do not emit in our band. Yeah, so we're more concerned about, right, the multipath, the reflections, that kind of thing. So it's actually the OrbCom communication satellites that for some of these radio telescopes doing these 21 centimeter measurements, they can be very messed up by OrbCom.
Yeah.
Could I jump in with a question here?
Yes, please do.
Wood and edgewise. There's a second project going on at Avro that's also looking for radio signals from the early universe. Professor Kieran Clary is prime investigator for COMAP. And this project seems to have some of the same concerns. The early period, the assembly of galaxies, but he'll be looking at emissions originating with carbon monoxide. Can you talk about what's the trade-off?
Yeah, absolutely. Yeah, so that's a really exciting project. They've come out with a lot of early papers demonstrating that their techniques are working and that they're getting limits on the signal. Yeah, so like Steve just said, this is looking for emission not from neutral hydrogen, but from carbon monoxide. The challenge of that approach is that that signal is actually even more faint than the neutral hydrogen signal, but there's less contamination. And so it's unclear to me kind of, you know, if we're considering this a race of, you know, what emission line you're looking at, which one is going to win out. Right, there's certainly, you know, you need more raw sensitivity to look at carbon monoxide, but your filtering problem is going to be a little bit easier. Yeah.
Okay, thank you very much for that. Are there other questions? Anybody else? Dr. Gaster, you had a number of questions in the chat, most of which I didn't particularly understand. Again, being a history major. You want to jump back in?
Sure. I think she answered a couple of them. And she answered almost immediately upon my posting. She answered the RFI one, and there was some discussion about that. She talked about the lunar bases and the universal problem of who's going to fund that. Let's see, I asked about the simulations, were they fully general relativistic or Newtonian, and she wasn't sure. But it was a great talk, and she answered pretty much all of my questions. Thanks very much.
I see one question in the chat. Is the minimum detectable signal consistent with what you need to observe? I'm not sure I fully understand that question. I don't know.
Oh, yeah.
Yeah.
So if you looked at all the sources of noise and the capabilities of your receiver, you know, you're going to have a minimum detectable signal. And so is your system, you know, able in its current configuration, if the signal were you know, actually there, would you be able to detect it?
Right. So theoretically, we expect that we have the raw sensitivity to do this. So we should be able to, you know, we have enough antennas based on our expected just thermal noise. We expect to be able to measure the signal. The problem is what we call systematic error, which basically means we're messing up. That there are stages in the analysis where we're getting leakage from our contaminants into the signal we're trying to measure. So this could be, you know, from a number of mechanisms. One that I think about a lot is calibration. So we need to calibrate these telescopes very, very precisely. And what happens when you have small errors is that you take this foreground signal, you know, the close by galaxies, the Milky Way, that kind of stuff, and you have a pretty good expectation or understanding of what that signal looks like. But if you haven't calibrated your telescope properly, that signal doesn't look the way you expected. And suddenly you're not able to remove it properly. So it's those kinds of problems that are currently the limiting thing. It's not just sheer raw sensitivity. Yeah, so it's really about this careful analysis and this ability to disentangle these different signals and understand, you know, exactly what the signal looks like hitting the telescope and exactly what the telescope's doing to it in the data pathway.
So I apologize if you mentioned this in your talk, but you just mentioned calibration. What source do you, or sources do you use for calibration?
So traditionally, this telescope, and for other science applications, this telescope uses Cygnus A and Cassiopeia A for
Okay.
calibration. So these are just poundingly bright radio sources
Yeah.
that we can use to calibrate. It turns out for this kind of very precise measurement, we need to go even deeper than that. And so as many sources as we can get. So we use enormous galaxy surveys, also mapping of large scale radio structures on the sky. We just kind of take all the information we can get about the sky and input that into calibration.
Sounds great. Well, this is really exciting work. I wish you much success.
Thank you.
I have one question. Has there been any, I guess, advancements in using AI for calibration and filtering systems as far as algorithms or
That's a good question.
items that may take, I guess, human minds, months or years to do? And not that I'm saying that's the way to go, but just a thought.
Yeah. So a lot of these techniques are, if not explicitly machine learning based, very machine learning adjacent. So there's been some work, really trying to plug our data into a neural network and say what cosmological parameters can you estimate based on that. And as far as I know, they haven't, come up with great results. That's not really surprising because neural networks tend to work very well for more well-defined problems. There's also been machine learning tackling RFI flagging that's been pretty successful. In terms of calibration, the techniques we're using are more maximum likelihood optimization problems, Bayesian statistics. So we can use, Bayesian statistics to impose priors about what we expect the sky to look like, what we expect the telescope response to look like, and then kind of solve this whole maximum likelihood system of equations to actually calculate the parameters of what the instrument's doing. Does that answer your question?
Yes, thank you. Thank you very much.
Let me ask a facetious question in a way. So no one has actually detected these very highly redshifted 21 centimeter signals.
Mm-hmm.
And I'm looking at the acknowledgements in the team. So when you do detect them, who on this chart gets the Nobel Prize?
That's a good question. Yeah, so this team is the full over LWA team. And this is, an observatory that has a lot of different science goals. So the 21 centimeter cosmology team is really led by Caltech and ASU. So the PIs of this project are Greg Hallinan and Judd Bowman. So they're kind of leading the 21 centimeter effort, along with myself as a postdoc.
So we're talking to Jocelyn Bell Burnell, potentially.
One can hope.
Only successful this time.
Hi, Dr. Byrne. To follow up on that, how certain are you that it will be detectable within your lifetime?
Oh, that's a good question. Right. I mean, you can never be 100% certain. How certain were scientists that we could detect gravity waves within our lifetime? So this is a similar kind of problem where with, gravity wave detections, there were many years of fighting these systematic errors, doing really precise stuff. And you kind of the team had to have faith that it was going to pan out, that they were going to get these systematics down to the point that they could make the detection, and they were successful in that. In terms of this science, I think the best understanding we have of the trajectory is looking at the progress that's been made in the last decade, 2 decades, that kind of thing. And that's really mapped out by these upper limits. So we can look at a plot of where the upper limits on the signal were over time. And they've improved by about 2 orders of magnitude in the last 10 years. So the very first generation of these experiments placed, very high upper limits, very unconstraining limits on the signal, and we've improved a lot over that. So if that kind of progress keeps up, I expect we'll have a detection, certainly within the next decade.
That would be awesome. Thank you.
I think one of the ingredients, of course, in a project like this is funding. And California has a friend in Washington who maybe we should be lobbying, or you and your group should be lobbying like crazy. It's Senator Alex Padilla. He was a mechanical engineer. He's a graduate of that other very good technology school that resides on the East Coast.
Which one is that, Mike?
Well, take a guess. He's a friend of this kind of technology projects, and I don't know how Caltech does its lobbying, but they should be talking to Alex Padilla. He's potentially a friend. I'm not sure exactly what committees he's serving on, but he might be of help in terms of getting the funding, which would speed up, I think, the process. More money often, not always, but often speeds up the process.
Certainly, yes. And, I want to remind people this is their taxpayer money at work. So I hope I don't let down the taxpayers.
You're not letting down the taxpayers. There's a lot of benefits that come out of this kind of research. Just for example, training. You're probably working with graduate students. You're training those graduate students. That's a benefit to the state of California and to the whole country. So you're not letting down the taxpayers.
Well, are there any more questions? I think we need to start wrapping this up. Professor Byrne, you've been very generous with your time. Let me ask maybe 1 or 2 more questions.
I guess I see this question in the chat that I missed about the coaxial cables versus the optical cables and the transmission rates of those. So that is definitely something that affects the signal processing, and one of the reasons why calibration is so important. So one of the things we do in calibration is understand the exact timing of each of the antennas and how it relates to all the other ones. So we have a term in calibration, which is, if you have a source at X spot on the sky, radiating down, being coupled into the antenna, at what point are we actually recording that signal? And that enables us to do this proper, correlation of all the different antennas.
Well, with that, again, Dr. Byrne, thank you very much. And I think we had a wonderful discussion here. Appreciate your time. And with that, let me mention something about our next Greenway talk. Greenway talks online will continue on Saturday, September 24th. Richard Ellis, professor of astrophysics at University College London and former director of Palomar Observatory, will provide a contrasting view of the early universe as seen by a veteran observer working primarily at optical and near-infrared wavelengths. His presentation is titled Quest for the Cosmic Dawn, First Results from the James Webb Space Telescope. So Again, thank you to Dr. Byrne. My thanks as well to all of you for attending and supporting the Greenway Talks online. I'll say goodbye. And
Thank
with
you
that,
so much. Thank you all.
thank you.
Really good.
Thank you.
And with that, I'll close the meeting and we'll see you again on September 24th. Thank you, everybody. Bye-bye.